Normalement, ça va changer. D'ici il y a 2 secondes, 10-15 secondes. On dira. C'est bon, ça diffuse. Bon bah ça marche, ça tourne. Allez, à plus tard. Ouais. Ouais. C'est bizarre,
ça correspond à peu près à l'image qu'il y a déjà sur l'écran. Et sinon, si on se met le niveau de la caméra, il y a un moment, il ne peut pas que Hervé. Ah oui, tout le monde. Si je fais coucou, tout le monde.
Pour l'instant, il y a 4 personnes. Je vois pas l'heure.
Bon, alors, on va pas avec les masses.
PhD. Normalement. Là, tu vas partir quand tu vas démarrer.
Du coup, j'ai donné
Tu l'as donné à qui?
tous mes papiers. Du coup, il y a le truc. comment dire. Il y a un manuscrit ici pour qu'il puisse le partager. Non, mais il y en a un autre qui en a un, et j'ai des gens, moi je leur ai envoyé un mail en disant est-ce que vous voulez que j'en imprime un ou pas, et ils m'ont tous dit non, sauf un, du coup j'en ai imprimé un. Et le reste, il y en a un autre qui chez Napoléon qu'elle fera passer normalement dans le public.
Je l'ai vu un.
Et moi j'en ai un.
C'est comme ça.
Je suis le seul à avoir demandé un manuscrit, c'est ça?
C'est ça, voilà. Après, je peux être déplacé. Hein. Je crois que j'étais en charge du président.
Allez, d'accord.
Continue dans quel ordre là? On va faire l'ordre des questions, ce sera un truc qu'on a fait à Lyon, voilà, c'est assez, tu tranches dans l'ordre des questions. Ouais, c'est pas mal ça.
Si vous
Oli,
voulez,
elle sera sur ses écrans.
en premier, Nicolas.
Ensuite,
Ensuite, ce sera Lionel. Et puis après, c'est vous.
après c'est toi.
Ah, tu veux, d'accord.
Après c'est toi. Après c'est toi. Je finis un dernier. On va faire Romain ici. C'est bon, ça se passe. Vous avez le ventre bien rempli et.
Mais non, parce qu'ils nous ont invité à 20 endroits. C'est vrai. Donc, du coup, on n'a pas pu jouer la gueule. On n'a pas pu voir la gueule.
Ça va bien.
Ouais, c'est pas vrai. On a peut-être dépassé 20 ans.
Non, non, c'est vrai.
Je reste en vrai. Merci.
Moi, je n'ai pas fait ça.
En plus, la caméra.
C'est chaud, hein.
Où la caméra?
Ça, je pense que c'est tomber le. Ça maintenant.
T'es trop émotionné.
Bah ouais,
C'est clair aussi.
Je conflicte sur l'écran quand tu fais pas la visio. Ça va être bien maintenant.
Est-ce que les notifications. Ça paraît encore qu'il faut faire ça à peu près.
Même quand ça vibre, ça peut se faire. Oui, encore les 23. Tu vas pas commencer.
Non. Mais du coup, comme j'ai rangé mon téléphone,
On va voir ça.
C'est midi.
C'est bien de commencer à 4 heures. Ça, on n'a pas stress. Non, je veux dire, tu vois, on arrive des minutes avant, c'est aussi très important.
Et Romain,
Il avait imprimé un truc. Romain,
il
est
gère
là
son
pour
stress, lui
mettre
aussi.
un petit stress. Non, Romain, il fait exprès de retenir la rétention exprès. C'est droit, c'est gourde.
En fait, je ne suis pas comme ça, donc propriétaire de notre salon. Je pense qu'il faut que Romain se connecte et aussi. Et je ne sais pas s'il doit l'accepter ou si c'est le
Là, je veux dire qu'il faudra qu'il est sur l'ordinateur.
Je sais pas parce que là, enfin, non, parce que tout à l'heure, j'en ai pu connecter, je pense qu'elle a juste coupé son micro. Et je
pense qu'elle est connectée là, mais elle n'a juste pas mis sa caméra.
Mais tu l'as vu tout
à l'heure. Non, ça n'a pas bougé en tout cas. Il n'y a pas de caméra. En tout cas, j'en ai eu accès sans mot de passe.
Si toi tu peux mettre ta caméra, elle devrait pas commencer. Hein?
27.
Okay. Daniel, tu peux vérifier après avec qu'elle fasse un petit coucou au début, Oli, parce qu'elle n'a pas mis sa caméra, je pense.
Normalement, là, de toute façon, on entend tout le monde ici. Quand on parle, elle devrait entendre.
Hello, Holly, do you hear us?
Yes.
Ah, cool. Okay. We already have a few minutes before beginning.
Okay.
Si j'avais pas note, je n'ai pas d'autres questions.
Si quelqu'un arrive après, il peut toujours rentrer par là. On peut la laisser une fois à la
Peut-être tranquillement. On va encore les 2 dernières minutes. Ça y est, enfermé.
C'est d'abord celle de gauche, et ensuite.
Non, prends ton pad.
Non, j'ai une minute.
Minute, ça va pas chez là. Plutôt en arrière.
Bon, je fais le temps des 2 dernières minutes, juste une toute petite introduction. Bonjour tout le monde. La soutenance aura lieu en anglais. Et la raison, c'est que la collègue qui est à l'extérieur ne va pas parler facilement. Bien que j'ai pas trop de doute sur le fait qu'elle comprenne un certain nombre de nos mots, je ferai l'introduction en anglais directement. Everybody's ready? Okay. So first, let me thank you for being here. I'm happy to be the president of this jury. My name is Menevaux, professor at the University of Poitiers. And the jury is composed by Rushmeier, professor at Yale University, Nicolas Holzschuch, research director at Inria Grenoble, Lionel Simonot, researcher at the University of Poitiers, Mickaël Ribardière, also researcher at the University of Poitiers, Romain Pacanowski, researcher at Inria Bordeaux, as well as Pascal Barla, researcher also at the University of Bordeaux, Inria Bordeaux, sorry. And you have 45 minutes for your defense. So from now.
Thanks. Okay, hello everybody. Thank you for the introduction. So today I will present the work I did over 3 years, which is entitled Micrograin Formalism for the Rendering of Porous Materials. And this work was supervised by Pascal Barla and Romain Pacanowski at the Inria of Bordeaux and the University of Bordeaux. So my work takes place in the discipline of computer science dedicated to the generation of images, which is computer graphics. And computer graphics is used in many areas, such as video games, architecture and design, automotive industry, or scientific visualization, and many more. The appearance modeling is central to all of these applications, and it is a specialized area within computer graphics that focuses on simulating how light interacts with different surfaces. As you can see in this image, there is a wide range of appearance to be modeled, from the car paint to leaves, from natural objects to human-made objects. During my PhD study, I worked on the appearance of porous materials, and porous materials are everywhere. For example, here you have a subset of them with regolith, sand, rocks, and in that case, the pores are the spaces between the grains. The pores can be found at various scales, from the nanometer level to much larger form, and our focus in this work is on pore at that scale larger than on micron, where the impact on appearance can be directly modeled using geometric optics. So there is different sizes. As you can see, also there are different colors, and this is due to the fact that they don't have the same composition. Also, we may have different packing. Here, for example, with the footstep, and the surface will appear brighter since the surface is more packed due to the footstep. So there is less projected shadow on the surface. So those 3 elements are appearance parameters. The porosity is not restricted to volume. I also worked a lot on porous layers. Porous layers are layers made of particles that are on top of any materials. Here, for example, you have dust on light bulb, or or pollen on cars. And one common aspect of those examples is that we need to define how light interacts with those objects. For example, here at grazing angle, we will mostly see the dust layer or the pollen layer, since they are masking the underlying material. In computer graphics, the appearance of opaque materials is defined by the bidirectional reflectance distribution function, which in short is the BRDF. And this function defines how much energy coming in from an incoming direction gets reflected in an outgoing direction. In my work, we split the different types of BRDFs in three main categories. The diffuse BRDFs, where the light is reflected without a preferred direction. Here, for example, it is a Lambertian, which means that it is perfectly diffuse. You may have glossy BRDFs, where the light is reflected around the specular reflection direction, or retroreflective BRDFs, where the light is reflected back toward the incoming direction. However, in most real-world materials, they exhibit a mixture of those different categories. For example, we may have diffuse plus retroreflective plus glossy BRDFs, or any kind of different mixture. The idea of BRDF model is that they define how light interacts with micro details that are not visible from the observer. And there are many ways to describe those macro details. For example, we may have a night field for surface-based BRDF, or a random field of spherical particles in the case of volumetric BRDFs. So to give you a little bit more background on volumetric BRDFs, there is the spherical scatterers BRDFs, where the idea is to have an infinite amount of microsphere in an L space. And we can control their appearance, but also their spacing, so the porosity. However, we need to have an infinite depth of those spheres, so we are not able to model porous layers, for example. And the resulting BRDF is diffuse only. The good thing is that it is quite efficient to evaluate since it is analytic. On the other side, we have the microflakes, where the idea is to have randomly scattered flakes and randomly oriented flakes. We can also change their appearance, and we can control their density, so the porosity inside this medium. The issue is that there is no closed form evaluation of this kind of structure, since we need to do the light transport simulation inside that structure, since it is stochastic. The good part is that we can have arbitrary appearance with those type of BRDFs, and we are not restricted to diffuse BRDFs. Then, for the surface-based BRDFs, we mainly have and mostly have the microfacet theory, which describes the interaction with light of the light inside an eye field. And to do that, we need to describe the orientation of the microfacets. And this is done using the normal distribution function, the NDF, that can be seen as a normalized histogram of the different microfacet orientations. And the wider the distribution is, the rougher the object will look. And if we flatten the surface, you can see that the object will appear shinier. And this can be seen in the normal distribution function, since the NDF will be sharper. So the reflection will be sharper as well. Once we define the orientation of the microfacet, we also need to define their visibility. Some may be visible from the light and the view. Some may be shadowed by the eye field or masked by the eye field. And the ratio of the microfacets that are visible or not is given using the geometric attenuation factor, which is also referred as shadowing and masking function. So here, for example, with a set of normal M, the geometric attenuation factor will give us the ratio of micronormal that are visible from the direction given by the green arrow. And with this graph, if we use its complement, we can get the quantity of interreflection inside the eye field. So now we describe the orientation and the visibility of the microfacets, and we only need to define their reflectance now. For example, we can assume that they are, the light is reflected based on a Fresnel mirror. So it is reflected on the specular direction based on the microfacet normal, and the intensity will be the Fresnel reflectance. Or we can have diffuse microfacets, but in that case, there is no analytical solution until we do some hypothesis on the distribution of normal or the geometric solution function, or if we are doing more approximations. There are also surface-based porous Ribardières. The first one was the model of Menevaux and colleague, which proposed to add cylindrical pores inside the microsurface. And this will transform a dense BRDF into a porous one. And this implies an increase in the contrast of the diffuse lobe due to interflexion. And this will also reduce the intensity of the specular lobe. Unfortunately, this model is empirical since it is based on simulated data. There is also the more recent work of Dion and colleague, which proposed to have a roughness that depends on the height of the height field. And something great about it is that we can have we can assign a specific color to a specific height. And for example, here you have blue diffuse microfacets on top of red diffuse microfacets, and this will create grazing angle color changes. So as you can see on the nose of the dragon, at grazing angle, only the blue diffuse microfacets are visible, since they are the one on top of the height field. However, since it is based on the microfacet theory, we can only there is only an analytical solution for specular microfacets. So if we map the two parameters of roughness and porosity in a 2D map, our hypothesis is that there are the spherical, the volumetric models that are working well for high roughness and high porosity, and the surface-based model that are working well for any roughness, but only for very low porosity. So the question is how can we fill this gap? The first thing we did is a numerical analysis of porous appearance models. We made the assumption that porous material can be represented by sphere aggregates, and notice here that the sphere may intersect. We can control the filling factor, which is also the complement of the porosity, by changing the radius of the spheres. We can also control how flat the spheres at the surface are, by setting with anfractuosity or without anfractuosity. And we can change the micro BRDF that we assign to the spheres, for example, the glossy BRDF or diffuse BRDF. Something that we saw quite early in our test, and that is specific to those kind of porous material, is the opposition effect. Here, for example, for the reflection configuration, there is nothing special to see, but if we look at the retroreflection configuration, when the light, when the direction of illumination is aligned to the direction of observation, there is an increase in brightness, and this is due to the fact that the shadows are no longer visible. The protected shadows are not visible, since it is masked by the geometry itself. So with the geometry, we assigned it a micro BRDF on it, and we can do light transport simulation inside this structure. We accumulate the outgoing rays with their contribution, and based on that, we can reconstruct a macro BRDF that is based on the micro BRDF and the geometry itself. So here, for example, for a geometry of sphere aggregate of blue diffuse sphere aggregates, with the BRDF simulation, for each angle of incidence, we will get a simulated BRDF slice, which is in polar coordinates, so with theta the elevation and p the azimuthal angle. And as you can see, there is the opposition effect that is visible here in the retroreflection configuration. With the simulation, we can also split the different light paths. For example, we can split the light paths based on the single scattering or the multiple scattering, or the light that are only intersecting the the spheres on the top for the surface, or the light paths that are going inside the volume for the volume part. Based on those elements, so we want to evaluate the different models. So we start from the simulation, and we will instantiate the model parameters based on the geometry and the microBRDF that we use for the simulations. So in that case, we use the spherical scatterers, since we are using sphere aggregates, so the model of Abke and Dion. We take the absolute difference of the simulation and the model, then the log of the mean square of those differences. And this gives us an error metric that we can map for various filling factor and different angle of incidence. So now we have an error map, and this error map can be split in the single scattering and the multiple scattering from the light path partition. And something that we can see, that we can already notice, is that most of the error is coming from the single scattering, since the intensity of multiple scattering is often smaller. So now we compared the simulation with the models, and what we saw is that for low filling factor, the different models are matching really well the simulations. However, as soon as we increase the filling factor, the models are starting to mismatch with the simulations. And that's the case for the long version microBRDF, but also for glossy microBRDFs. One observation we did is that the error pattern is similar to the pattern found when we computed the integral of the simulated BRDF restricted to the surface interaction over the simulated full BRDF. And this suggests that most errors are coming from the surface interactions. From which we can conclude that if we want to reduce errors at low porosity, we need a better modeling of surface interactions. That's why we decided to develop a surface-based model that is specialized on porosity, and this is what led us to the development of the micrograin formalism for porous layers. So what is the impact of porous layers? First, it may reduce the transparency. For example, if you have fingerprints on smooth glass, it can create grazing angle color changes if you have a dust layer on a car or pollen. Or you can have hazy reflection in a case where the roughness of the porous layer is different from the roughness of the base material. Overall, the addition of porous layers enable the addition of imperfections on arbitrary surfaces. So here is our micrograin structure. Here you can see an explicit realization of them, but keep in mind that they are never visible. So similarly to microfacets, it is a stochastic geometry. It is a structure made of opaque ellipsoid, and we can change their appearance, so they can be diffuse, plastic, or metallic, but they all have the same appearance over the distribution. We can control also how flat they are with the anfractuosity parameter. And regarding their size, we can change their radius, but we assume that they are always greater than the wavelengths, such that we can consider the geometric of them. And they are also randomly scattered using a uniform distribution of density rho. And based on the radius and the density, we can compute analytically the filling factor, so the coverage of our porous layer, which is tau 0, which is also the complement of the porosity. So now, how can we model the impact of a micrograin layer on top of a base layer, any base material? First, we only consider the single scattering, such that we can easily split the light path between those that are interacting with the micrograins and those that are interacting with the base layer. So we have two weight functions, WS and WE, for the porous layer and the base layer. And those weight functions depend on the visibility of the micrograins. And they are weighting the micrograin BRDF and the arbitrary based BSDF. For the micrograin BRDF, it is a diffuse term plus microfacet-based specular. And since it is microfacet-based, we need to define a new distribution of normal and a new geometric attenuation factor, which are our two main contributions. So let's first start by looking at the derivation for the distribution of normal. So here we look at an explicit realization of micrograins, and let's start with the point on the surface, and we want to assign it a normal. The idea here is to project vertically the surface point onto the micrograin, but in some cases, like here, as you can see with the yellow dots, there are multiple intersections. And the right intersection point will always be the one on top of the layer, so on top of all the micrograins, since it is the only one to be visible from the top. In our example, it is the intersection with the left micrograin. We observe that the vertical projection of the surface point is always on the closest grain. So from the distance to the closest grain, we can compute the normal with the mapping function. To compute the distribution of normal, we first look at the distribution of distances to the closest grain. To do that, so we start by looking at the distribution of micrograin from the top, and we will only look at their centers. And here we want to know what is the likelihood that a random point x is at the distance r from the closest micrograin center, C star. We can do it by computing the Voronoi diagram and by taking the histogram of the different distances. But luckily for us, we can also do it analytically using the first order statistics. And this gives us our distribution, so P1 of r, which is the likelihood from a closest point to be at a distance r, given the density rho of the distribution of points. Once we have this distribution, we can integrate it toward the radius of our micrograins. And by doing so, we are computing the ratio of the points that are inside or outside the micrograins, so the filling factor of our porous layer. Once we have our distribution of distances to the closest grain, we want to transform it into the distribution of micrograin normals, so the NDF. We start with the point x on the surface. We assume that it is inside a micrograin, and we know its likelihood to be at a distance r to its sensor. We also know the mapping function from the distance r to the normal m, and now we want to know what is the likelihood of that normal. We computed this distribution of normal with a change of variable from the PDF to the NDF based on this mapping function. And all the details are given in the manuscript. So now you maybe have an idea of how we computed this distribution. The issue here is that we only have a control over how flat the micrograins are. So we can only simulate isotropic BRDFs. However, we saw that this distribution is shape invariant, so we can directly extend this distribution to anisotropy. So rather than having a compression factor on the height of the micrograins, we can have two stretching factors in the tangent and bitangent direction, so beta x and beta y. Now, for the geometric attenuation factor, we have two solutions. The first one was that we developed was the Smith gap. However, one of the main assumptions of the Smith gap is that the height and the normal are not correlated, which in our context of micrograin doesn't make any sense, since our distribution of normal is built using this exact assumption. Also, we are not able to take into account the correlation between light and view directions. And our solution was analytic, but we didn't have a closed form evaluation of it, so it was not so much efficient to evaluate. And now we also have the exact gap that I will present just after, and it has some nice properties. We are taking into account the correlation between height and normal, but also between light and view. It is analytic and closed form, so efficient to evaluate. And since everything is correlated, we can have a reflectance that depends on the height of the micronormal or even the micronormal itself. To compute this exact gap, we first had a key observation on the filling factor. We saw that our equation of the filling factor can be generalized to a general filling factor. So here, with this equation, we can compute the filling factor of an arbitrary shape only by knowing the density of the distribution and the area of one element. But remind that this equation is working as long as the elements are randomly scattered using a uniform distribution. So as you can see here, when the video is zoomed out, the real filling factor converges toward the estimation which is computed with this equation. This equation is very important since it will enable us to compute the visibility of the whole micrograin distribution only by knowing the visibility of one and only one micrograin. So now for the computation of the unidirectional graph, we want to know what is the probability for a ray leaving the surface at a point of normal m in direction I to be intersected by the micrograin layer. The first reason can be that the ray intersects the starting micrograin. Luckily for us, it is really easy to compute since it is only the heaviside function of the dot product between I and m. So we want to make sure that the I direction is on the hemisphere defined by the m micron norm. The second reason can be that the ray intersects the other micrograins, and it is the probability that we call G1 dist for distant micrograin. So for a random point of normal m, we want to know the probability that it is visible. For example, here it is visible, here it is not, and here it is. Intuitively, G1 dist corresponds to the probability of a point being in the shadow of the other micrograin. And this is where our observation on the generic form of the filling factor comes into play. With the general filling factor equation, we can compute the probability for a random point to be out of all the micrograin shadows only by knowing the area of one micrograin shadow, which is sigma s. So to give you a little bit more detail on sigma s, it is the area of the projected shadow in direction I of a spherical cap cut by a plane of height h. And this is what you can see here with the side view, where a plane of height h cut the shadow volume. And when we look at that from the top view, so by looking at the micrograin from top view, this cut will create this pink lunar shape, which is the micrograin shadow at h, and we want to know its area. Something that I really like about this formalism is that we can give a geometric intuition to nearly each element that we are computing. And since we have a geometric intuition, we can easily decompose our shape into multiple or simpler shapes. For example, the pink lunar shape, we decompose it into two ellipse sectors and two triangles. And their area can be computed identically. Now we want to compute the bidirectional graph, which is the probability for a ray leaving the surface at a point of normal m, this time in direction I or O, to be intersected by the micrograin layer. So the first idea is just to simply multiply the two unidirectional graph, which give us this equation, where we add the area of the shadow in direction I in red, and the area of the shadow in direction O in green. But as you can see, in some cases, the shadow may overlap, and in those cases, the attenuation is overestimated, since it is in those cases that the directions are correlated. So in order to take into account this correlation, we must subtract the area that is counted twice. And it is the area that we call sigma intersection, the intersection of the two shadows. So what we are computing here is therefore the area of the union of the two shadows and not the sum of the shadow areas. Once again, we have a geometric decomposition to compute sigma intersection, and once again it is analytic. So now I describe most of the elements for the microfacet-based specular, so the distribution of normal and the geometric attenuation factor. And the missing part is the diffuse term. Here we use directly the Heinz and Dupuy tech report that was used for diffuse microfacets. But we simply needed to use our own distribution of normal and geometric attenuation function. when we compute for the computation of the global illumination, we need to generate direction, which in the case of microfacet or our micrograin model, require the sampling of micronormals. The basic solution is to generate micronormals in the proportion of the normal distribution function. But when we look at the surface at grazing angle, in some cases, the generated normals may be back-facing, which create invalid light paths and supplemental noise. To solve this issue, we also developed a sampling routine for the visible normal distribution function that takes into account the visibility of micronormals with the GAF. And with this method, less samples are wasted, which reduce the noise for a constant time rendering. So maybe you will be able to see it here. So when I swap between the two cases, so without the visible normal distribution sampling, so here there is less noise than here with a constant time handling. We did extensive validation of the different functions that I presented. So for the visible filling factor, the distribution of normal, the geometric attenuation function for the different versions, and the whole BRDF. And something that is really great is that when we are doing simulation on explicit realization of our micrograin layer, there is a nearly perfect match between the simulation and our model. Now to show you some results. So we first look at the GAF comparisons. So here you can see a sphere lit in retroreflection configuration. It is a diffuse sphere with gold micrograin on top and with a filling factor of 0.2. And here a very small unfactorizity. We will compare our Smith GAF with our height-only corrected GAF and our full exact GAF with height and direction correction. Here you can see that there is not so much differences, but when I increase the height of and the unfactorizity of the micrograins, you can see that for a large unfactorizity, our exact GAF will produce a lot more retroreflection than the previous Smith GAF. And I think that this is where our micrograin BRDF get very different properties than previous work, such as microfacets. And here, the row on the bottom is the flip comparison, which is what you may see if you flip between the different images or the different version of the GAF. To compare our model against previous work, so on the left you have the Mary and colleague model, and on the right the Dion and colleague models. For a low filling factor, we saw that our model is closer to the Dion and colleague model. However, for medium filling factor, so 0.5, this time the Mary and colleague and Dion and colleague model are closer between each other. While our method should produce more reflectance at grazing angle, and this is due to our exact GAF. Regarding the expressiveness of our method, so here you have the base material on the top, so a full absorber, a plastic and glass spheres, and we had on top of that our Lambertian micrograin layer, this time with a medium filling factor and a high unfactorizity. And as you can see, it will create grazing angle color changes, or in the case of for the glass sphere, it will also reduce the transparency of the glass. So with that, we can simulate, for example, dust deposits. This time with a larger filling factor and a smaller unfactorizity, it will also, and for gold micrograins, it will also create grazing angle color changes, but it's more subtle for the two cases, but it will also create hazy reflections since the roughness of the micrograin layer is different from the roughness of the base material. Now I will compare the two different versions of our exact GAF. So here it is a gray diffuse shape, and we add on top of that gold micrograins. And look, when I change when I add the correlation in direction, here you can see that there is not so much differences. Maybe for you it's invisible. But it is because we are not in the retroflexion. When we are in the retroflexion configuration, you can see here that the impact of the, when we account for the correlation direction, it can make a huge impact on the visuals. Here, it is just a simple blue inversion on the shape. And when we add on top of that blue diffuse micrograins, you can see that there is less contrast now on the shape. And this is due to the fact that there is less projected shadows. And this phenomenon is getting even worse in the retroreflection. As you can see, the contrast is much lower when we add blue micrograin on top of the blue shape. Here, there is, so it's 3 different balls with 3 different filling factors. And maybe you should look at the bottom left instead. So we had anisotropic red diffuse micrograin on the shape. And what I show you is that what here I show you what happened when I rotate the micrograin by 90 degrees. So when I swap the refractivity parameters, and as you can see, the visibility of the micrograin layer gets modified based on that. Here we use a pair of orthogonal anisotropic micrograin layers. So we have an anisotropic red plastic micrograin layer on top of an anisotropic green plastic micrograin layer. And when I rotate the object, you can see that at grazing angle, and maybe you should look at the right instead. The red micrograin will be more visible in different directions than others. It's the same for the green micrograins. We can also change the reflectance of the micrograin based on its micronormal. Here, for example, we have diffuse micrograin, but there it is green on the bottom and red on the top, and this will create a very thin red outline, and it will be orange for the rest. We can also set the color red to for the left part of the micrograin and green for the right part, and this will create anisotropic behaviors even if the micrograin is isotropic. And we can also do the same to control the index of refraction for conductor micrograin in this case. We can change the parameters specially. Here, for example, we have a dust layer on wood, and we add more dust when the normal are facing upward. Here is the same, but we are using plastic-like micrograins, green plastic-like micrograins on glass. Or we can also model dirt, for example, inside fibers. Overall, our model have an 8 to 20% overhead compared to the classic microfacet models. So, so it's possible to run and to use it for real-time rendering. Something great is that the filling factor can be filtered linearly. So we can use the classic MIP maps to control the filling factor parameter. And we can also use the classic roughness map that are used to control the refractivity parameter. So here the frame rate is capped at 60 FPS, but we can get more. So to conclude and to give you some perspective on the micrograins, so we where's water? Okay. So we developed the micrograin formalism, in which we introduced the concept of visible filling factor. And based on our micrograin layer and the visible filling factor, we derived the porous normal distribution function, as well as its geometric attenuation function. And we have two solutions for that, the Spitz-Gaff and now the exact gaff. And based on the exact gaff and the porous normal distribution function, we can compute the porous visible normal distribution function for an efficient imported sampling of this model. Now, regarding the limitations, there is no closed form evaluation for diffuse micrograins, which is the same limitation as for classic microfacet BRDFs. And we didn't compare our work to real-world acquired materials, but I will talk about that just. We are not able to compute the multiple scattering inside the micrograin layer. Because this requires to sample the visible normal distribution function inside the micrograin layer, and we don't know how to do that right now. So we need to sample the next intersection points given the previous intersection based on height and a new direction. But for now, we can only sample the visible normal distribution as long as the starting point is outside the micrograin layer. We want to bind our micrograin layer with volumetric models, and here the idea is to reduce the error maps that I showed you in the beginning of the talk, where we saw that most of the errors are coming from the surface, and now that we have a model that is really specialized for surface porosity, we want to bind our micrograin layer on top of volumetric model, and we hope that it will reduce the error. We already have some ideas to do the binding. For example, we have a link between the filling factor for the micrograins, so the surface filling factor, with the filling factor inside the volume. We also want to work on inverted micrograins. So here the idea is to have micrograin holes. We already have the normal distribution function for that, since it is the same as for the classic micrograins. The only thing that will change is the visibility, but we think that the visibility for inverted micrograins is a simpler case than and something that we already defined in the visibility for classic micrograins. We also want to have diverse micrograin profiles. And here it will require to change the mapping function from the distance to the closest center to the normal. And this will create a new distribution of normals, but also it will change the visibility of the grains. Well, the main goal here is to be able to have polydispersed micrograin distribution. So to have multiple sizes of grains, multiple appearances, for example, transparent micrograins, where the hope is to be able to match polydispersed micrograin distribution to real-world surfaces. And by doing so, we think that it will be easier to match our model with polydispersed micrograin to real-world acquired. And the final extension to the micrograins is that we want to have a non-uniform or random distribution of micrograin. The issue here is that we will not be able to use the equation of the general filling factor anymore, since it assumes a uniform random distribution. And here, for example, it is a Poisson distribution, and I simulated the distribution of distances to the closest grain that you can see with the red cross. So at the beginning it's linear, so we have an analytical solution for that, but for the rest of the function, we don't have an analytical solution, so we have no way to compute right now new distribution of normals and another general filling factor equation for this type of distribution. Thank you all for your attention. I hope you liked what you saw, and here for the questions.
Thank you very much. now we are going to let some room to the questions. Usually, the first person to ask the question is a reviewer, and we choose the furthest one. So please, Holly, you have time now for your questions.
Thank you. And first of all, a wonderful presentation, and it is a thrill to see a dissertation with no mention of machine learning. It's wonderful modeling, and it's wonderful validation with the ground truth simulations. That being said, you started with the dirt on glass and the pollen on the car. How would I even go about, as pollen and dust are not spheres. They aren't ellipsoids, half ellipsoids. When they fall on things, they don't interpenetrate. How would I even go about estimating what properties I should use to try to do a predictive model of the appearance of dust that settles on something? I could do a simulation and get some sort of distribution. How would I get the information to apply this model to see if it's accurately predicting the appearance?
Okay, thank you. So yeah, of course, our micrograin can intersect between each others, and well, we didn't do any comparison against so real-world acquired materials, and the issue here is that well, not an issue, but I think it's similar to microfacets, where in the real world we don't have real microfacets, and our hope is that even if the structure that we are modeling is not exactly the same as in reality, it will be able to simulate similar effects, even though it's not the same. So similarly to microfacet for rough material, for example. And to estimate, for example, the filling factor of a dust deposit on a car, maybe we should look at the distribution itself that can be found in reality, in real world, and based on that, we can, I think, approximate the filling factor and use this filling factor inside our model to use our model. I think it's my answer.
Okay, thank you. Well, that was my major question. I guess another one is the potential, another kind of porous surface is, and they have the flake model for fabrics, but you could think of something like velvet as a surface with a porous layer of cylinders on top of it. Could your model be adapted to modeling something like velvet?
Maybe, yes. The main issue here is that we don't have multiple scattering, and when you have cylinder-like micrograins, you have an reflectivity that is really high. So there is a lot of interreflection inside the layer, and since we are only modeling the single scattering, you will have a lot of energy loss. So right now it's limited, but if we if we develop the multiple scattering, I think that this model could work really well for this type of tiny fibers on clothes.
Okay, thank you. Those were my questions.
Okay, thank you very much, Ali. The second reviewer is Nicolas Holzschuch.
Thank you very much. I have a few questions. One is going to be easy. I'm going to start with the easy ones. At some point, you said when you looked at your simulator, which is, by the way, great work, most error, you can see clearly that most errors are coming from surface interaction. And I'm afraid I would like you to explain to me again how I could see that clearly, because it was not fully clear for me. If you could.
Yeah, I will try. Okay, I think it's on this side.
Something like that, yes.
So here, and so you have the error pattern that is here. It's for only one simulation, but this pattern is similar to the other simulation that I showed. And on the right side, we computed the integral over the Ribardière slice of the Ribardière restricted to the surface under the full Ribardière, which gives us the ratio of the energy that is coming in, coming in from the surface. And what we see here is that when we increase the thin factor, of course, most of the energy will come from the surface. So it's what we see here when it converges toward 1. All the energy is coming from the surface. And so this pattern for us is similar to the one that is here. And of course, it's the same when you increase the angle of incidence. You will mostly see the top of the volume, and the light will not go deep into the volume. So most of the energy will come from the surface.
So you're saying that they're correlated, therefore there must be cost.
No, it was one observation, and that's why we said that it suggests that most of the error are coming from the surface.
The thing is, if the energy is bigger, the error will also be bigger, because you have more chance of making an error of 10 if you're measuring something that's 10,000 than if you're measuring something that's 1.
Yes, but maybe there is a lot of error inside the volume, but if there is not so much energy in the volume, it's not that bad if the model is not really efficient. Well, I think that most of the error, most of the energy is coming from the surface, and it looks like it's maybe the error may be coming also from the surface. If we want to have a large impact on the error, the first thing we have to do is to work on the surface.
Okay, thank you. And I have another question. Much later in the presentation, you mentioned the diffuse term for the micrograins. And where would that diffuse term be coming from?
I'm not sure to understand the question.
If I look at the surface, usually the diffuse term would be coming from interreflection at the microfacet level. But what's making something diffuse at your micrograin scale? Would there be some microfacet on the micrograin?
I think it depends on the scale of the grains. For example, here you with the rocks. To me, each rock is not a conductor. It's more something that is diffuse. From my point of view, I think that it will depend on the level of simulation, but I don't see why each micrograin couldn't be diffuse. Or
let's put that differently. Was that something? Was that a hypothesis you needed in order to fit with the data, or just something you added because it's nice to have diffuse BRDFs on the micrograins?
No. So we did not use any real-world data.
Yes, that's my next question, by the way. But
and so we, for the simulation, we use the same hypothesis than our model. So we generate a geometry that is have the same properties than our model. So with the filling factor, the refractivity parameter. And then we can choose which microbial depth that we assign to the spheres. So if we assigned diffuse microbial depth on the spheres, well, of course, we want to have a micrograin model that have a diffuse term.
So yeah, spoiler alert, but yes, my next question is about comparison with real world data. You're probably expecting that. Do you have any hints? I know you didn't do it, and I understand that there are many good reasons for that, but do you have any hints as how with real world data?
No, I have an intuition of how we can do it. But the result, I don't really know. I hope it will work perfectly, but for the generation of those results, my idea, the thing is, you need to have a base material. So you are not longer working with one unique material. So you have our micrograin layer and another material. So the idea is how can we control this model such that the error that is coming from the base material model will not contaminate our evaluation of micrograin model. So my idea was, for example, to just compute the appearance on a perfectly clean surface. Get this appearance, and then add dust on it or pollen. Based on that, we can control the base material and evaluate our porous layer model. So I think it needs to be a two-step evaluation process, two-step process.
I'm stop here because I see the president is getting a choose.
The president is fine.
So can I have another one?
Sure.
Okay, so and my last question then is you briefly mentioned wavelength effects at the beginning, but never came back to it. Do you have any intuition about how the model would expand with wavelength-based effects?
No, not really. Well, I think one of the most important assumption of our model is that we are distributing the spheres randomly. And I'm not sure, but I think that if we are distributing the spheres randomly, it may break the different interference that could happen. But I'm not sure.
Let's put that as future work.
Yeah.
Thank you, Nicolas. Ali, we were wondering if you were waiting for a new turn of questions.
No.
No? Okay. Okay. The next one for the questions is Lionel Simonot.
Thank you, Daniel. I really enjoy reading your thesis, and thank you for the quality and clarity of your presentation. It was really nice. I particularly appreciated the consistency of the manuscript. Regarding ERDF models, I agree with Oli. It's often said that everything has already been done, and that the only way forward is deep learning. And I appreciate that you work challenge this idea. Over where I have a few comments and questions. So I found that maybe that your thesis lacks a clear definition of what you consider a porous material, because your approach is specific and may differ from how it is understood in other scientific field. Could you clarify your definition of porous materials, and do you think your model is general enough to represent different types of porosity?
So we mostly worked on sphere aggregates. So for the simulation, so we use sphere aggregates, so in randomly scattered spheres in 3D. And then we restricted ourselves to only spheres scattered to, on the surface plane. And this is what we considered as porosity. But of course, there are a lot of different ways to have porous materials. This is why also I talk about inverted micrograins, since, for example, if you have inverted micrograins, you may have holes and create holes inside the structure, which can account for porosity due to insects or water that is coming in the surface. But yeah, it was a computer graphics thesis, so I didn't do any. I didn't define clearly porosity, but what we considered as porosity is the spacing between the elements. In our case, the elements was the spheres or the ellipsoids.
Thank you. The use of aggregating ellipsoids to represent the porous layer is really original, and it allows a smooth transition to a continuous layer, opaque layer. And this reminded me of coalescence and percolation models for thin film formation. And could your approach be adapted, for example, by imposing volume conservation during aggregation between two particles, like in formation?
I'm not sure to see.
Particles aggregates.
Yes.
Keep the volume.
Volume of each of the
volume of the aggregates is equal to the volume of particles.
Well, the filling factor is based on can compute the filling factor, the density of the grains and their radius. So we know the area of each particles, but to compute the area of the whole distribution, I'm not sure we are able to do that. I think it's maybe in relation with the distribution of the grains. Yeah, I don't know. If you're sure that the grains are not intersecting, there's no problem to compute the area. But right now, I'm not sure.
Okay. The model you developed with this precise consideration of coverage rate and geometric attenuation factor, really, I find it really a remarkable achievement in both geometry and computation. Congratulations for that. It's really impressive. You mainly present results for flattened particles, and my question is, are there any limitation when beta fructuosity is greater than 1?
No, theoretically, there is no limitation, so I think the maximum that I used in the papers and in the manuscript was an height of 3. And I think it was there. So this type of grains. But the issue is that if you have even higher grains, you will get more interreflection, so more multiple scattering. And since we are not accounting for this, a lot of energy loss. And we did some tests, but at the point, the surface will just be black since there's too much interreflection.
Okay, and this is my next question, because you emphasize the importance of interreflection between particles very well. The effect can sometimes be more significant than the effect you model, and they are very difficult to model. do you think it's possible to define a relatively simple model that could account for both layer discontinuities and interreflections?
So when we did the simulation for the validation of the model, we did simulation for the single scattering, but also for the BRDF, so single plus multiple scattering. And we saw, but we didn't show it a lot, but the shape of the reflectance, well, the shape of the BRDF is also quite special for this type of structure. For example, we are not able to just say that the multiple scattering is the same as a weighted single scattering, and just adding the different terms. Since the shape is different, we are forced to. I think that if we want to make some approximation, we can do fitting of BRDF, classic BRDF lobes on the multiple scattering. But what we saw is that the shape of the BRDF of the multiple scattering is very special.
There is no simple solution.
Simple solution is great.
For diffuse particles, I wasn't fully convinced by your first approach using only a Lambertian contribution. I was much more enthusiastic about the second approach, considering particles as truly Lambertian, taking their shape into account, even though it involves a much more complex integral to be computed. Have you compared these two approaches with the same shadowing function? How significant are the differences?
The only comparison that we used was this one, but it's not that clear. Well, it's not a global elimination, so to see the differences, it's not really easy. But the issue is that we, if I remember it well, we are not just able to swap the different geometric attenuation function, since it requires to change also the different mix functions. And if we don't change the mix function, it will create, it will break the energy conservation. So we may have a variation of energy if you are just using the Smith graph in our formulation with the exact visibility. So maybe that's something that we missed to compare the different version of our model, but just changing the different graph is not enough. We also need to change the mix functions.
Okay, and my last question, in terms of future work, I'm particularly interested in the possibility of extending your model to account for volume distributions. Many highly matte opaque materials, such as spectralon used for reference whites, are porous, and their photometric response is often challenging to model, as it deviates from the purely Lambertian behavior. Could you elaborate on how you envision this extension, and what challenges do you anticipate in accurately modeling such complex photometric behaviors?
Yes. So our idea was to. So we evaluated the Apke and Dion volumetric models, and we saw that when the porosity is high, they are very good. So our idea was to use them as the base material, and then put on that our micrograin layer. The thing is that now we have to bind the green factors, so the quantity of sphere need to match, and we also need to bind their appearance. For the case of the volumetric models, the control is over the phase function and I think it's the asymmetry of the phase function. and the diffuse albedo, I think. So we need to instantiate based on our micrograin parameters. So if they are diffuse or floating, we need to transform those parameters into a phase function, into diffuse albedo, to bind the different reflectance of the spheres. And after, so for the geometric parts, we need to bind the filling factor. But now, the filling factor, so the zero here for the filling factor of the surface is two-dimensional, while the volumetric filling factor is three-dimensional. So we have to do something to match, to be able to match them. So maybe we can assume, we can say that let's assume a slab of a specific height, and we count the number of particles inside this slab, and we project each of those particles on the surface. We have our number of particles, and now we can compute our filling factor for the surface. So there are multiple ideas to be able to bind those models. But the thing is, I think for the spectralon, it is very thin, very tiny particles, and I don't know if there is any interference effect inside the spectrum. And if it's the case,
Okay, thank you very much. To conclude, I must say that it is really excellent work, both in terms of its scientific depth and the clarity of the presentation. So, congratulations.
Thank you, Lionel. The next one is Mickaël Ribardière.
Thank you, Lionel. Thank you to invite me to your PhD defense, and thank you to Pascal and Romain to invite me in your micrograin adventure. I have many questions about the perspective work, and I hope we will continue to collaborate all together to work on these things. I have just two small questions. At the beginning of your talk, you show a picture of Unreal Engine. So you say, okay, graphics is for games, and your model is derived after a lot of mathematical derivations. So do you think your model is artist friendly? For instance, compared to the model used in computer graphics like the Disney model?
When you have the Uber shaders with 10 parameters, yeah. Why not just add another one? Yes, I think the only parameter that we are adding is the filling factor, since the infractuosity in fact is very similar or the same as for the classic roughness. So the roughness can be used, the infractuosity can be mapped with the roughness. So we can already use the tools and the texture that artists are using for the infractuosity. And for the filling factor, I think it's can be easily used. For example, here with the car, you have some projection with the wheel on the side of the car, and I think there is already a texture that is defining maybe just an alpha mask or something, but you already have texture that may define those kind of filling factor. So, well, it's of course it's slower than previous work, slower to microfacet models, but I think the elements are already here to be used in real, well, in the industry. I think the missing part is the multiple scattering with slow integration.
Do you think there is multiple scattering here?
I think, yeah. Not sure, but they are pre-computing a lot of stuff. So, yes.
So is it possible to pre-compute multiple scattering?
It's always possible to pre-compute.
Yeah.
To be efficient in storage, I don't know.
my second question is about the Smith graph. It's clear we never find a pure analytical derivation of the Smith graph, and more important, it's really not good, as we can see in your results. So is it useful to?
No, well, maybe for someone it can be useful, but
in your model.
I think it was the first step toward the exact graph, and it would have been too difficult to publish something with already the normal distribution function, the exact visibility, the exact graph. We did the right choice to just split into first the distribution of normal, then simple visibility term that we know that will work with, so with the Smith graph, and after with the idea of the exact graph.
Okay, so thank you. It was a pleasure to work with you.
Thank you. I am going to take the floor for a few words and questions before leaving it to the supervisors. First, thank you. I have read the report, and I found it very well explained and presented. That was really great. Thank you also for the presentation. I will have a few questions also, and I would like to get back to the measurements and comparisons with real surfaces, because you can try to measure a BRDF and then try to fit the parameters of your model. So that would be a choice. But if you want to get deeper into the details, you would probably also like measure the parameters. Do you think it could be possible, and could you imagine something that could help to do that?
Yes, I don't know, if you have a picture from the top of a perfectly smooth surface, and if you had dust on that, you can take a second picture and take the difference, and you will see, I don't know, maybe the number of pixels that changed, and based on that you can estimate the fill factor of your redistribution of points. But I don't know if it's.
Do you think it has a chance to fit with your model or any other one?
And yes, I think if there is one model that will work well, it's mine. You know, I don't know what is the influence of different distribution of grains in the real world. So maybe it will work for. Maybe you need to double the filling factor to match the reality, or you need to remap the filling factor to get a mapping between our model and the reality. But I think it will also depend on the size of the grains. There is more things that will get an impact on.
I would see many issues in that, because first you would need to have the exact BRDF of the, let's say, substrate. And that is quite complicated, in fact. And also I was wondering about the shape of the micrograins, because I'm not sure that dust, as said Holly before, could efficiently be represented by let's say spherical caps or approximations. So I'm just not sure.
The thing is, for of course, particle in reality are facets, and it's not perfectly smooth shapes. But in the world, they are all oriented differently. We are not seeing them very close, so the different orientation will be mixed, and I think that it's the fact having a proxy with the shape of an ellipsoid. I'm not sure that it will be an issue for that, since you want to have the mean reflectance of geometry.
Maybe the mixture would fit. Yes. Okay. Another question also concerning the comparisons, because you mentioned the models by Meriou et al. And Déon et al. And I think it can be a short question, in fact, because how could we consider in such a comparison that a model is better than another one? And what are the criteria? What is your feeling about that?
First, they don't have the same approach for the modeling. Meriou and colleague, it was in 2000, so now I think in their paper the macrofacet theory is not even described. Just and the main issue I think for in this work is that it's based on they assume they use a geometry of pores and they doing simulation inside this cylinder. So you are not free to change the shape of the cylinder or have control over the geometry. And for the Dion and colleague approach, I think it's really great. And right now, if I have to choose between Meriou and Dion, of course I will choose for the Dion model, since you have the possibility to compute the multiple scattering. Most of the time it will not be native, but we already have the tools and we know how to do that. And something great also is that you can change the distribution of normal, you can change the visibility based on the distribution of normal. So you have a lot of tools to have an impact on the final appearance, while for the Meriou and colleague it was not the case. And for our method, the thing that I like the most is that you are not longer working with randomly oriented microfacets, which in fact is more like a medium than the real surface. With our micrograin model, you really have the reflection that is defined by randomly distributed ellipsoid, and they are really here. It's not completely a random shape with only the distribution that is considered.
Okay, and one very last question. If you had time now for some months, what, in your perspective, what would you choose to work on for the next weeks and months if you could engage?
I think I would like to work on multiple scattering.
That would be first choice.
Multiple scattering or polydispersity. If I want the model to be used in the future, I think the multiple scattering is a must-have.
Okay, thank you very much. The two supervisors, Romain or Pascal, who would like to be Romain?
Thank you, Daniel. So I will say nice words in English, less nice in French. Just kidding. No, it was amazing what you did past 3 years. I've been impressed, like all your stuff you did technically and scientifically. So it's been a great pleasure to work with you, to see you even teach me some things. So this is a very good defense, of course, in my opinion. And what is the level of this defense is that some of the questions I'm really glad you are the one that are going to answer them. So again, congrats.
Thank you. Pascal?
If you don't mind, can I switch to French? That's all of you.
That's okay for me.
Ok, bon, moi je me suis régalé avec toi, comme que ce soit dans les brainstorms, même à la deadline, ça a bien marché, et puis au baby-foot aussi. Et donc ça a été un plaisir de te voir progresser dans les 3 domaines. Moi au baby-foot. Si. Et pour finir, je dirais que je suis convaincu que tu pourras faire une bonne carrière dans le domaine, très bonne même. Je m'envie de recollaborer avec toi et de refaire des parties de conférence.
Okay, merci Pascal. Thank you. Now we will have to deliberate. What is the plan? We stay here? No.
Stay here and everybody gets out. And we
Il est
don't...
prévu que la délibération ait lieu nos conclusions, Simon Lucas, donc vous avez réalisé une présentation claire et de grande qualité du contexte du sujet et des contributions scientifiques, avec une attention particulière pour détailler les dérivations mathématiques des modèles que vous proposez. Vos contributions sont originales et de qualité. Elles permettent de définir une représentation efficace de l'apparence de surface à l'aide de distributions de micrograins. Et pour cela, vous avez développé pendant la présentation, justifié et validé chaque élément de votre modèle, c'est-à-dire la distribution normale, la fonction d'ombrage et de masquage, ainsi que les manières de réaliser les calculs d'échantillonnage d'importance pour la résolution numérique de l'équation du transport lumineux par méthode de Monte-Carlo. Vous avez présenté de nombreux résultats et en cela, vous avez démontré l'efficacité de vos modèles, tant sur les aspects visuels qu'en termes de performance de calcul. Plusieurs perspectives prometteuses sont proposées dans votre présentation, avec des pistes de réalisation concrètes. Vous avez su répondre de manière rigoureuse, argumentée et convaincante aux questions nombreuses et précises du jury. Et le jury note que la thèse ouvre des perspectives qui semblent très prometteuses pour le domaine de l'apparence des matériaux en informatique graphique. Et donc, pour toutes ces raisons, le jury vous décerne à l'unanimité le grade de docteur de l'Université de Bordeaux. Félicitations.
Ouais. Je lis maintenant. Ok. En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête de savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Un mini,
Ouais, si tu veux faire un discours, vas-y.
Okay, mini remerciement pour, enfin, je sais pas. Mais ouais, bah déjà merci à Pascal et Romain qui m'ont très très bien accompagné dans cette aventure. Ils sont partis aussi beaucoup pour ma réussite. Merci à eux, merci à Gary Gilling qui sont arrivés avec moi. C'était très cool d'être avec vous aussi pendant cette période. Merci en fait, à tous les membres de Menevaux globalement, Morgane qui était là aussi pendant quelques temps, Pierre qui ensuite a pris sa place, et Otto qui a pris la place quoi. Aussi, bref, tout le monde, merci beaucoup d'avoir été là dans l'équipe Menevaux, c'était très agréable, l'ambiance était très agréable, une bonne émulsion scientifique. Quoi ouais, puis merci à mon entourage, ma famille, Mickaël, mes parents, ma sœur, voilà, qui m'ont très bien entouré aussi pendant cette période-là. Et merci à tous aussi d'être venus, ça me fait plaisir que vous soyez ici nombreux. Et si vous avez faim, soif, je crois que c'est le moment maintenant. Merci.
Je vous laisse dire un mot à Molly. Je ne sais pas comment ça se passe.
Pour elle.
C'est toi qui as sa procuration et que voilà, c'est bon.
Okay.
C'était un des
pour elle.
qui t'a donné.
Molly,